Welcome to Presentation 38. In today's presentation, I'm going to be talking about the RFID, which is the radio frequency identification. Now, the RFI is part of our layer 3 architecture. From layer 2, we're going to be using the UART framework, SPI framework, and the I/O ports. Now, the agenda for today, first I'm going to go through a description of the RFI receiver and transmitter. Next, I'm going to talk about code development, go through a sample program, and finally we'll go through the summary. So let's start with the description. So the system is composed of a transmitter and receiver, which in our case is going to be the RFI RC522. And also there is a tag. Now, the reader, what it does, it generates a 13.56 megahertz radio frequency. Now, when the tag comes, is radiated by that radio signal, it acts like a power receiver, converts the radio waves into electricity, stores enough energy to run. So basically, the tag doesn't have a battery, and it only comes alive when it's exposed to the radio frequency generated by the reader. Now, the role of the microcontroller will be to initialize the reader, of course, then command the RFI reader to transmit data to the tag, which may be stored in the tag, and also command the RFI reader to get data from the tag. Now, there are a couple of documents that we have to be concerned with. The first one is the radio. The radio specification data sheet, which is done by the manufacturer, is put together by, I should say, by the manufacturer of the RFID, in our case, the RC522, as I mentioned. And also there are requirements for the tag. Now, the manufacturer of the receiver and of the tag may not be the same. So there is an extra document which guarantees that this all played together, and that's the ISO/IEC 14443. This is like a two-party contract. The reader and the tag must both implement the same layer. So let's look at the documentation that we need to consider. So as usual, based on that documentation, I created a couple of frameworks. I should say 3 frameworks. So from the data sheets of the MFRC522, I generated two frameworks. One which is going to corresponds to the commands that we need to send the MFR522. And the other one is the different registers that we are going to have to manipulate to make things happen. The third data sheet, I got it from the ISO 14443. There were some commands there that the controller must generate, and I have it enumerated here. And for example, it's the REQA and WUPAB, and all this will become familiar to you before we are done. So that's all. I don't want to spend a lot of time in these documents because we have a lot of things to discuss today. So if you look inside the tag, what you're going to find is this table. So the tag has a 1 kilobyte of memory, which would be 1024 bytes which stores this particular table. Now, this table is composed by 16 sectors, and each sector has 4 blocks. And each block has 16 bytes. Now let's look at sector 0. So let me back up. So when the tag gets close to the reader, what's going to happen is that we are going to read information of these sectors and blocks, and we're going to decide to do something. For example, we may decide to open a door, we may decide to do some transaction and increment and decrement things. So all is going to be contained on this table, and we'll be able to read and write to this table according to certain rules. So let's go back to sector 0. Let's look at sector 0. Now in sector 0, what you have is the NUID in manufacturer's data. The NUID is the number that identifies the tag. So if you want to talk to a unique tag, you need to first find out what its NUID. Next, we have a couple of data blocks. That's where you can just write any data you want. And then block 3 has the key A, the access parameters, and key B. Now I'll be talking about each of these elements. Now, sector 1 through 15. So first we talk about sector 0 because it's unique, because it has this block 0 with special information. Now let's talk about block 1 through 15. Now, what it has is it has the, you can store data. So for example, you could have a block 4, 5, 6, you can store data. In block 7, you're going to have key A, access, and key B. Now, how this works is when you are going to communicate with the tag, eventually you're going to have to send back and forth some information, and where you're going to send the key, which is going to allow you to do things to this card based on the access. Now, every time you want to access a different sector, you have to go through that same drill, sending the key and getting authorized to read or write into that particular sector. So let's look at this thing. So let's look at the data block. Now, a data block, which are in this case Frosu 6, 1, 2, 56 or 58, can either store a 16 bytes of ordinary data, can be text IDs, configuration, etc. Or can be used as a 16 bytes value block with a fixed internal format. So basically, you can store the data in a data block any way you want, or you can store it with a particular format, which is called the value block. And if you store it with a particular format, then it becomes a value block. Now, the tag doesn't know that this is a value block, except when it reaches and sees the format. It says, oh, okay, this is a value block. And value blocks are going to have different access characteristics than the regular other data. So let's look a little bit closer at the value block. So a value 16 bytes block uses a fixed structure for reliability, and safety. So if you have something important, then you have to make sure that you use this type. The idea is that the tag gets closed. So you could say, for example, that the tag shows that you can access 16 times to a, let's say, a car wash. You have a card's access to, you can do 16 car washes. Well, when you go in, we're going to have to decrement the number that you have left. And every time you go in, we decrement the number till you get to 0, and then the card is no good anymore. So that transaction has to be done correctly, and you have to make sure that this is guaranteed. Because you're going to access your tag, and then you can remove the tag. And if you remove the tag at the wrong time, well, things may not get completed. So you have a particular format that guarantees that the transaction has been done. So when you use a value block, all you have is you can store a 4-byte numeric value. When you use a regular data, you can use any way you want your 16 bytes. In the case of a value block, you only have 4 because of the format you have to use. The remaining 12 bytes are used for redundancy, inversion, and address check. So this structure basically enables safe increment-decrement operation, as I noted, and protects against data corruption and power loss. So let's see what the format looks like. So a value is basically it's going to have your 4 bytes, which is the data, the value that you're interested. Then it's going to follow by the 4 bytes, which is the NAT of that value, the inverse of the value. Then it's going to be followed by the value again, and then you're going to have the address, the inverse of the address, and the inverse of the address. So it's somewhat of a complex structure, but that makes sure that everything matches. And if the reader sees this format, then it knows that it's dealing with a value, and it's going to check the access bytes to make sure that everything is correct, or you have the you can have the rights to access that data. So let's look at some of the parameters. So let's start by key A and key B. And next, we're going to deal with the access bit, which is the permission. So basically, this is going to tell you this is what you can access, and then whether you have the right key to access, then they'll allow you to do it. So let's look at the key A and key B. Think of them as a password, basically. Default is going to be FF, and used to read data, write data, change permissions. So if you want, every time you want to read, write, or change permission, you have to have a password. Now, which password will allow you to do what is contained on the access bit. Oh, I forgot one item here. If you lose the key, forget the key, the sector is permanently locked. So if you do anything here incorrect, you lost your sector. Okay, let's talk about the access bit. It tells you who can read a particular sector, who can write to that sector, who can increment and decrement. Now, the access bits are valid for the whole sector. So if you, for example, say, hey, I want to read as block 5, and you authenticate for block 5, by doing that, you are going to be able to read block 5, but you'll also be able to read 6 and 4. And it also, so we can increment, and then it tells you also who can change the keys. So let's see how this works. So access bit permission, who can read, write, increment, decrement, change keys, as I noted. Okay, so here we go. So you have 3 parameters. According to the value of those 3 parameters, you're going to be able to read, write, increment, decrements. So for example, if all are C, then you're going to be able to read with key A or key B. So if you have either of the keys are correct, then you can read, write, increment, decrement. Now, if you have a 0, 1, 0, then what you have is you can do key A or B to read. Then to write, you must have key B correct. Increment, decrement, never. So let's look at a different. So this is for the data. You have, these are your, how you can set those C1, C2, and C3 parameters. And then you never do this because it locks you out. If you put the correct C1, C2, C3, you just lost your block. Now, if you have a value block, so if you store your data in the format that I told you for a value block, then it's going to read it and it's going to spec the access bits are going to be according, the access is going to be according to how the C1, C2, and C3 gets formatted, but it's different than for the data. So you have only two options. So you have key A only for increment, decrement, write, you never write. And then if you have this, then you're going to have a key A or B decrement. So that's for this. So we have a C1, C2, 3C for regular data, for value blocks, I should say for regular block data. And then now we have for the sector trailers, who can modify, for example, here bit 7, we have a different set of C1, C2, and C3. So let's look at this thing. So now what I want to do is I want to, if I look at the sector, the way I'm going to define this is going to be block 0, 1, 2, and 3. So for the purpose of this C1, C2, and C3, I'm going to say this is blocks 0, 1, 2, and 3. Now, for each of these blocks, I'm going to define the access. Now, for block 0, my C1, C2, and C3 is going to be C10, C20, C30. For block 1, it's going to be C11, C21, 631. And for block 2, it's going to be C12, 22, and 32. So I have my 3 blocks here. Now, for the trailer, which is block 3, 0, 1, 2, 3, I'm going to call it C1, 3, C2, 3, and 3, 3. Now, these are the parameters. So I did not say how, I haven't mentioned how we're going to store all these things in these 4 bytes. I'm not there yet. So if any of these blocks are data block, then the value C1, C2, C3, which are these values, are going to be driven by this table. If I have a value, this can be value according to how I stored the data, then these are the C1, C2, 3C access, which is define the access. And finally, if I have for the block 3, which is C1, 3, 2, 3, and 3, 3, the sector trailer are going to be like this. Okay, so now we have those parameters. We know what value we want to set these parameters. So if I want block 6, so this would be block 0, 1, 2, then if I decide, hey, I want to never be able to increment, decrement, then I'm going to put a C1, which would be C12 would be 0, C22 would be 1, C32 is going to be 0. So that's how I go about setting up this. So I can do this first. So next I'm going to have to figure out how do I take all this data and place it on the different access bytes. So there is a format for that. So here we have it. The bytes, so the data, once we define the access characteristics, then we have bytes 6, 7, 8, and 9. We have to place all that data there. So how we do that? So the standard says how to do that. So byte 6, basically you are going to put NAT C2 and NAT C1. Byte 7 is going to be C1 NAT C3. Byte 8 is going to be C3 NAT C2. And byte 9 is going to be C1 and C3. So what does byte 6 going to look? So we define what are these C23. So it's going to be NAT C23, NAT 22, NAT 21, NAT 20, NAT 13. So it's going to be NAT of all the parameters. So the chart before we decided what this number should be, and now we need to place them on byte 6, 7, 8. Byte 7 is going to be C13, 12, 11, 10, and NAT 33, 32, 33, and 30. Byte 8, you can see, is going to be C3, 33, 32, 31, so forth and so on. And finally, byte 9 is going to be, as I have it here, C13. So anyhow, first we went and looked at, hey, what are these values should be to provide access? Then, once we decided that, then we go ahead and put this together. So now let's go to the code that is going to take care of putting together the access bits. Let's develop the code which is going to define the access to each of our blocks in a per sector basis. So let's assume we want to do for block 7 in this case, which we're working with sector 1, block 7. What we want to be able to say is that any parameter which are key A, access, and key B are going to be modified as long as we have a valid key B. So that means that we need a parameters of C1, C2, and C3 to be 0, 0, 1. Also, what we want to do is for block 4 through 6, we want to allow any modification to those blocks as long as you have key A or key B. And that means that C1, C2, and C3 have to be 0. So based on that desire, then we can create this particular matrix where we say for block 0, we're going to have C3, C2, and C1 parameters equal to 0. For block 1 and 2 the same, and for block 3 our C1 parameters, C3 parameter is going to be a 1, C2 is going to be a 0, and C1 is going to be also a 0. Now what I mean by 0, 1, 2, and 3 equate to block 4, 5, 6, and 7, being block 3 equal to block 7. Now, let's translate this these parameters into specific parameters for each of the bits in each of the 4 bytes. So we have C31 is equal to 0, 32 equal to 0, and 33 is equal to 1. So what this defines is block 31 is equal to 0, 32 is equal to 0, and block 33 is equal to 1. And we develop for this whole block, we develop for each of the parameters. Now we do that because we know that to populate byte 6, 7, 8, and 9, what we have to do is the following. Byte 6, as we already defined before, is negative C2,3. That would be a negative 2,3, I should say. So we come here, negative 2,3 would be this one. Negative C2,2 is right here, and so forth and so on. So now we started with this case, then we came down here, and then now we can define what has to go on each of our bytes. So let's look at the code. So the input to our routine are going to be these parameters that I show in this particular box. And let's go through our routines. So the first thing I do is I create the inverse of each of the parameter by using the exclusive OR or THOR. So we start by C1 inverse is going to be to C0, inverse 1, C2 inverse is going to be C2, and inverse of C3 is going to be C3, all THOR with the exclusive OR. So let's look at the bit 6. So what am I saying bit 6 is going to be? So the first thing is I take C2 inverted, and then I'm going to place it in location. The first time we go around, this I is 0. So C4, I'm going to place it in location 4. So it would be C2, 0, I'm going to place it in location 4. So that's what we're supposed to do. Negative inverted C2, 0 goes in location 4. Now I have C1, 0 that goes in location 0. So C1, 0 negated goes in location 0. So right now I place my negative C20 and I should say negation C20 and the negation of C1, 0 in bit 0 and bit 4, and that's what these statements are doing. Now I continue with the I equal to 0, so I have now C1, 0. Again, I put it in location 4 of bit 7, so that's 1, 0. And then the negative of, the inverse, I should say, of C3, 0 goes in location 0. So we have here 3, 0 goes here. And then we go to our last one, which is C3, which is 3, 0 goes into bit 0 of bit 8. 3, 0. So we have here 3, 0 goes in bit 4. And then we have C2, 0 goes in bit 0. C2, 0 goes in bit 0. Now, as I go through all these parameters, I'm going to end up completing my byte 6, 7, and 8, and then I'll place them in the access 0, 1, 2, and that's the output of this routine. So basically, let me recap here. So we need to calculate what are the bytes 6, 7, 8, and 9. Now 9, I haven't talked about 9 because really 9 we are going to put a default value, which is going to be 0, 1, 1, 0, 1, 0, 0, 1. It really doesn't matter at the end of the day what value we put here. There is no real requirement what to put in this byte 9. So all we have to worry is about these 3 bytes. So the first step is we go to our tables and see what we want these C1, 2, and 3 to be for each of our blocks, 7, 6, 5, 4, 5, 6, 7. That's going to equate to 0, 1, 2, 3, 7 being 3, 6 being 2, and for any block we do from the last one to the first one. And then we put the values corresponding to C3, 2, and 1. And then we break those values in each of the bits, the value of each of the bits for each of the parameters. And then we go ahead and follow this requirement, how the bits are supposed to be placed. Which means that we use the inverse of C2,3, which we calculated here. And then we go ahead to this routine that's going to put the data on the correct place. And then we end up with the access bytes, and that's what we're going to put in our access according to access for each of the sectors, according to what is the access we want to provide. So with this, we're ready to continue with our presentation. Okay, next I'm going to show, sorry about that. Next I'm going to show the code for the SPI communication. Usually we've done SPI many times, but this code, in this case, we require a little bit, some changes that we have to be aware of. So we're going to spend a couple of minutes looking at this code. So what we're going to discuss here, dealing with SPI, is the SPI format of the message. So the SPI has a 8-bit message, and the first bit is going to be the read or write control. Next, bits 1 through 6, I should say, are going to represent the register address. And finally, bit 0 is always going to be 0. So let's look at the code for the, let's start with the write. So when we are going to write, the first thing we need to do is we take the message and shift it to the left one bit. And we do that to ensure that the first bit is always 0. Next, what we're going to do is we're going to end it with the 7E, which that ensures that the first bit, the least significant and the most significant bits are both 0. Now at this point, we have decided that we're going to write, therefore the bit 7, which is the read and write control, has to be equal to 0. And then once we've have the whole message in the correct format, then we go ahead and do the transfer, which is just the typical transfer where we put the parameter into the SPDR0 to the data, then we wait for the transfer, and then we return the status, if any. Now let's look at the read. On the read is going to be fairly similar, except, so the first thing we do is we shift everything to the left to have our 0 bit, our bit 0 equal to 0. Next, we end it with the 7E, which ensures that the bit 0 and bit 7 are going to be equal to 0. And then we order the whole thing with 0 hex 80, which is going to put a 1 on the first bit, which is going to be a write. And then we go ahead and do the transfer. So it's straightforward. We just have to make sure that if we want to If we want to read, then we put a 1 on the most significant bit, which we do here. If we want to write, then we give the most significant as 0. We have to make sure that the bit 0 is always 0, so we have to shift everything left by one position. And that's all we have for the SPI formatting. So let's continue with the presentation. Okay, so let's next, what we're going to do is we're going to look at the code for initializing the RC522 tag and also the code for calculating the CRC. So up front, what I'm doing is spending a little time first on those routines that are helper routines. So for example, every time we send a message, we're going to require CRC. So let's look at the code that how we do the CRC, and then we have to initialize it. So let's go ahead and look at this code. So what I'm doing is I'm building the program a little bit at a time, and then we'll put it together. So let's continue with the code development. Okay, let's look at the code for initializing the RC522 reader. So what we have is a number of SPI writes. Now those parameters, I got them directly from the data sheet. So what you need to do is just for your unit, basically, as it's most of the time the case for initialize, you start by using whatever the manufacturer recommends. And then the last thing we do here is we go ahead and read the transmit control register. And then one of the things we don't want to do is we don't want to modify the whole register. We just want to modify a particular bit so we can get the antenna to be on, basically. So I get the data, then I send the transmit control register. I return it, but this time I OR it with hex 03, which is what's going to turn it on without modifying any of the existing data in the register, except for the one that I'm interested in, which is what's going to turn on the antenna. So that's all there is for the initialization. So let's go ahead and look at the CRC. So when we transmit messages back and forth to the between the microcontroller and the card reader, RFID card reader, we're going to have to provide as part of our message a CRC. So what we do is we send the data to the card reader and it calculates the CRC for us. So we don't have to have a routine that does that. So let's see how we get this accomplished. So of course we send in the data, the length of the data, and then the CRC is going to come back as a result. So the first thing we do, and it's going to be something fairly similar for all our, when we write and read to the reader. So the first thing we need to do is we need to stop any active command. So to send the reader basically to idle. So we do that by sending a hex 0 to the command register. Next, we're going to know that the CRC is complete and we can go get the data by looking at the reader registers. So the next thing we do is we clear all the all the interrupts. I should say interrupt register. So what we do is we clear all the CRC interrupts. Next, we're going to send the data. We want the card reader to calculate the CRC. So what we do, we just flash the FIFO to make sure we don't have anything there. And after doing that, the next thing we do is we go ahead and send parameter by parameter using this loop. We gave it the data, and the length comes from the inputs to this routine. So we go ahead and FIFO data register, we send all our data. After doing that, what we do is we write to the register hex 03, which is requesting that the CRC be calculated. And then what we have here is a timeout. I'm going to go through a loop where I'm going to be checking to see if the interrupt got triggered, and once the interrupt gets triggered, then I get out of the loop. But yes, in case something happens and something went wrong with the transmission, I'm just going to be a timeout, so I have a way of getting out of this do while loop. So basically, I get into the do while loop and I ask for the value of the interrupt register, and then if the value is hex 04, then I know that the CRC has been calculated, it's ready for me to go and get. So then I go ahead do two reads, one which is CRC result, register the low, register high parameters, which I'm going to call result 0 and result 1. So this is the most significant, the least significant and the most significant parameters. And then I go ahead and send the whole card back to idle so I can continue to use it. And then once this is done, if I have a timeout, then I will return a 1. If I return 0, that means that once I requested the CRC, I get a 0. Then I know I can look at my result and get the two parameters which represent the CRC register, CRC value, most significant, less significant bytes. So with that, we can continue with our presentation. Okay, so now we know how to calculate our CRC, which we're going to do whenever needed. Now, one of the things that we do every time we perform a read-write, we always want to know whether or not that got successfully accomplished or not. And what we do to verify that is we go ahead and poll the IRQ, the IRQ register, and according to the value of the IRQ is going to give us the information when those things got or not accomplished successfully. So let's look at that code. For many of our tasks, we have do while loop, and what we do is we go and check the interrupt status register to see whether or not the task had been completed. So we do this in a number of places. So what I've done here is created a routine which centralized that task. And basically we have 5 registers that gives us the status of our operation. So let's look at them and then we look at the code. So the first one we have the receive IRQ, which is bit 5, and when that gets set, then we know that the card sent a response, and the data is now available for us to get from the FIFO. So once that gets set, we know that we can go get our data. Next, I have the idle request interrupt, which states that the current command is done and the RC is in a idle state. So basically it says, hey, whatever it was supposed to do, it already did it and now it's in idle, just waiting for something new. Then we have the high alert requirement, bit 3, and then low alert, bit 2. And basically that's something that, as far as I can tell, nobody uses, but it says that the FIFO is getting full or the FIFO is getting empty. Next, what we have is the error interrupt, bit 1, which tells us that something went wrong. It could have been in CRC error, parity error, collision error, or buffer overflow. So then what you have to do is you have to check the error register to know exactly what went wrong. And finally, we have the timer IRQ, and basically it tells us that the
there has been a timeout and the card did not respond in time to our request. So we're in the do loop. If we get that, that means that's a timeout. Nobody's answering. Nobody's home. This is how we detect that there is no tag present. So let's look at the code that gets this accomplished. So we have a routine that we call. What I have here is a timeout of 20,000 cycles, but that's just the last resort. No, so first we go and we read the IRQ. Now, if the IRQ we ended with hex 1, that means that we had a timer timeout. That means that probably there was no tag available, and we had a timeout. So what we send out is we're going to send a return of 1. Next, if we get a IRQ, we end it when we get a hex 02 fault. That means that there was an error. And what we need to do is go to the error register and find out what that error is going to be related to. Next, we have an IRQ. If we get IRQ and we get ended with 030, and that's true, then basically that means that either the system is in idle, which is here, which means that the tasks already got accomplished, and also it may be that the card already sent there a response, and we have data on the FIFO. So basically, this means return 0. That means, hey, go get your data. And finally, what we have is our timeout. That means if nothing is happening, we don't get any of this error, and we get a timeout, that means we return with a 3, which is, this is software timeout. We don't know what happened, but we already did enough, we've gone around enough times. So that's kind of what I'm going to do when you see the RC522 wait for receive or idle. That's what we're going to be doing. So anyhow, now we can go back to continue to our presentation.
Okay. So now what I'm going to go, so we finish looking at the routines which are going to help us. So now let's go through the flow, how this is going to work, how the interaction between the reader and the tag or the card, you could call it can be tag or a card, and how is the flow and how things get accomplished. So what we have here is first the reader puts out an RF field, and it's constantly putting out that field. And when a card gets within the range, then the card is power up. Now, when we put out this field, which is constantly put out, we also put a signal, which is called an REQA or a WPA. That's basically a signal that is saying, hey, is there anybody out there? And anybody that is out there, please wake up. That's what what we're sending out. So there's a radiation field followed by a command that says, hey, any card that comes within this field, wake up. And now if a card has been halted, then it will only reply to a WUPA. So anyhow, we're sending these signals out. And then when a card or a tag gets within the range and wakes up, and it's going to reply to that signal with an ATQA. As soon as we get an ATQA, then the reader knows that, hey, there is a card, so let's do an anti-collision signal. Now, they call it anti-collision basically because you could have more than one tag at the same time. So you eventually are going to have to select between which card you want to talk to, but usually it's going to be one. So then what the card does, as soon as they get anti-collision message, what they they reply with the UID message and a BCC, which is like a OR, XOR of the UID. So when now the UID usually is 4 parameters, but sometimes can be 7 parameters. So that's why they call anti-collision 1, 2, or 3, depending on the number of parameters. But usually, keeping it simple, usually is 4. So you get your 4 parameters. After you get the UIDs, you could get more than one, I suppose. Next thing you do, you select which one you want to talk to. And once you send the select message, which includes the UID, then the card replies with it SAK, which means, yep, you've told me that you've selected me and I agree, I'll talk to you. Now, at this point, next thing we have to do is you have to send a message for an authentication request in the block you want to be authenticated for. So at this point, basically this is for the whole card as a whole, but then we get to the authentication where you're going to say, hey, I want to be able to do something to, now you talk about a particular block that I'm interested in. I want to read it, I want to write it. So then you send the block number, and the tag will reply with a random number, which the reader uses an equation which combines the key UID and the random number and sends it back to the tag or the card. And the card verifies that it gets the same number when it's running through the equation, and then signals it, okay, we've verified. Now, the authorization all the way to the verification, that's when you send your keys, and according to the keys that you send and what you're requiring and looking at the access, they're going to allow you to do things or not. So that's what we were looking at according to the access. So once you get verified, you are going to be able to read data, in which case you send the command to read the sector and the CRC, which we already know how to calculate the CRC. And then the card or the tag will send you the data back, which is always 16 plus the CRC. Or you can ask it to, you want to write something into a particular block, in which case you send the write command, sector, and the CRC, you get an acknowledgement back. And once at that point you get your acknowledgement, in theory, the data got written. But usually a good thing to do is you ask for, hey, I want to, oh, I'm sorry, you get the acknowledgement, then you send your data that you want to write. And after you send your data that you want to write, what you do next, and you command, you want to read the sector, and you send the CRC, and then you get this sector. So basically, hey, I want you to write, this is the data I want you to write, and then you read it back to make sure that everything got written as you expected. Now, once the transaction gets done, you need to halt the service. So for example, if you bring a card next to the reader, that transaction gets done, then you don't want the transactions to be done again. If you don't remove the card, you don't want the transaction to be over and over and over. So once the transaction gets done, then you set the halt. So you're not going to do anything to that card anymore. Now, if that card gets removed and loses power, then you can use that card again, because once you remove the card, it's going to forget about everything except for what got written into the into this database, into this table, you could say, to this table. So that's why it's important to halt, because if you have something that is incrementing, decrementing, and you don't remove your card, you don't want that to start decrementing, keep going decrementing. You decrement it once, you halt it. Then they're going to have to remove the card and bring it back in if they want more things to happen. So now I put the table here just to emphasize that every time we do every time we go from one sector to another sector, we have to go ahead and go through the authentication request. So all the way from REQA WUPA to SAK is for the whole card. Now from the authorization request down is going to be specific to a particular block. So let's look at the code for REQA WAPU for the anti-collision and for selecting the tag. Let's start by reviewing the code for the REQA and the WPA. So as the reader will send out the RF field, and that's going to power up any tag which is in the vicinity. So to wake them up, we need to send the REQA or the WUPA message. And we expect to get a return from the tag of the ATQA. Now, what if determines whether we're going to send the REQA or the WPA has to do with whether the tag was disconnected using the hold command or not. If it was disconnected using the hold command, then we need to send the WUPA, or in other words, it will only reply to the WUPA. So let's look at the code to start by the REQA. And this is going to be very common, the way we send the message. So the first thing we do is we send the card to an idle state. Basically, it says, let's start from 0, shut everything off. Next, we clear all flags. And we also flash the FIFO. So this is the housekeeping, you could say. Next, we send the REQA message. Now, this is considered a 7-bit message, so we need to send the bit framing command of hex 07. Next, we send the hex 0C, which is the transceiver, and the transmission is going to start once we set the bit 7 on the bit framing register. But we only want to modify bit 7. So what we do is we get the whole value of the register, then we OR it with the what's going to modify bit 7, and then we send it back. Now at this point, the REQ has already been transmitted, and we're waiting for the ATQA reply. So if our routine, which is the wait for RX idle, is not 0, then we return a 1. And also the REQA, the ATQA message has is composed, we're expecting to get two words. So if the reply in the FIFO, I don't have 2 elements, that means that something went wrong, and then we return with the 2. Otherwise, we have our 2 messages and we return 0. Now let's look at the WPA, which is going to be fairly similar. So let's do our housekeeping. System in idle, clear or interrupt flags. We flash the FIFO. Next, this is 7-bit message. We do that. Then at this point, we can send our WUPA message, which is hex 52. Next, we do transmit the data by sending the transceiver, and then we get our bit, modify our bit to start the transmission. Now at this point, this is exactly the same as we did before, except that we have 52. We send the hex 52 message opposed to the hex 26.
Next, what we do is we wait, and if the system did not go to idle, then it's still waiting, something went wrong. Next, we have our FIFO level. We expect to get two parameters. If we get anything less or more, then we have a problem. We want to return, we want to use that data. So finally, at this point, we know we're expecting to get two parameters, and we have two parameters, and we go out and return 0. So that's the first step. So let's look at the anti-collision code, and let's review it. So what we're going to do here is we're going to send the message, the anti-collision message, and we're expected to get the tag UID plus the BCC, which is the XOR of all the message as a check. So let's see how we do this. So the first thing we do is we're going to put the parameters in the buffer. The buffer 0 is going to have the cascade level 1, which is what we're interested in. Now, buffer 2 is supposed to have the number of parameters that we're going to send. So I'll explain this a little bit later, which basically says we're going to send 2 parameters. And I'll explain how this works. Let me see, maybe I have it here. Oh yeah, here I have it. Sorry. So the first parameter is the command. Now the second parameter, 2, means that we're going to send 2 bytes and 0 extra bits. So how does this work? So to send the number of commands that we're sending in, basically we send the second element in our buffer has to have the first most significant bits is going to represent the number of bytes that we're going to send, and the next least significant bits is going to represent the extra bits. So here what we're saying is, hey, we're going to send 2 bytes. So basically we have 1 and 2. First byte is the command, and the second one is the number of bytes that we're sending. Next, so let's start doing the housekeeping as before. So we stop any active command, clear the interrupt, clear the flash the FIFO. Now before we reset, we set the command to the command we said is going to be a 7-bit command. Now what we have to do is we reset it, because now we're going to deal with 8-bit commands. So we reset the bit framing, and next we start loading the data into the buffer. So we load the first element, which is the command, and the second element, which is the number of bytes that we're sending. Next we do as before. We're going to start the transceiver. We send the 0C hex, and then here what we're doing is we're getting the bit frame, and we're modifying only the bit 7 and sending the bit frame register back. So basically we're getting the register, modifying 1 bit, and then sending it back, so we don't modify anything else. Now here we're going to wait for our reply, and if it goes to idle, then and this is why this is important, is because the tag may have left, so we don't have any control whether the tag is going to be there or not. Somebody could just put the tag and then take it before. Something can happen that the transfer doesn't complete. So that's why we don't want to stay here waiting infinite. And then the next thing we do, we're expecting to get 5 five data elements back. So we ask, hey, is the 5 or not equal to 5? Then we have a problem. And we get out of here, we return to 2. Now at this point, we know that we got our 5 bytes. So we go ahead and take in, we read the 4 bytes, which represents the UID, which are 4. So we get our UID 4 elements. Now, I mentioned that we have to get the BCC. So we get the BCC from the, we request the BCC from the card, and then we calculated ourselves what that BCC should be. So the BCC should be the UID 0, 1, 2, and 3. We XOR exclusive all of them, and that's the result should be equal to the BCC. So then we ask, hey, the what we calculated is same as what we got from the reader. If the answer is no, then we know the data got corrupted. Otherwise, we know that everything's okay, and we return the 0. Now, I should also mention that here, the first element was a 93, which is the command, and the second one is the 2. I think I already mentioned it, so we're okay. So let's continue. So now let's look at the code for selecting the tag. So at this point, what we're going to do is select the tag, and then we'll get the SAK message back stating that, okay, we select you, and the tag said, understand, we're okay. So let's look at the message. So this is the selecting. So to selecting, we send the code 93, and then the number of bytes is 7 here. Again, what we did here is the most significant bits are going to represent the number of bytes we're sending, which are going to be 7, and no extra bits. So that's 70. So let's look at how we accomplish this. So we have the element 1, which is going to be 93, our buffer 0, our buffer 1 is going to be 7. So now we're going to fill up the buffer from 2 through 5. Basically, what we're going to do is we have to send we have to first send the whole UID. So that's going to take place here. So we have the cascade level command, number of bytes that we're sending. Then we go ahead and so we're putting together the message here. So what we do here is next is going to follow all the UID, saying, hey, this is the tag we're selecting with this particular UID. Then we have to calculate the BCC, which is the XOR, exclusive OR of all the UIDs. And then after that, we have to calculate the CRC, which basically is going to the CRC of what we have so far, which is the buffer, which has a 7 element, 4. We have 5 UIDs plus 2, 7, and then we're expecting to get the CRC. So part of the message, how we're putting it together is the command, number of bytes, the UIDs, the BCC, which is the XOR of the UID, and after that follows the CRC. So we have we call our routine is going to calculate the CRC, which is actually as a routine on the reader. And if that's successful, then we have our elements 7 and 8 are going to be CRC 0 and 1, which is the 2 elements that we did. Now, at this point, we have our message ready. So let's do the housekeeping on the fourth. So we send the card to idle, flash the FIFO, clear the register, do the bit framing, make sure we're using 8. And at this point now we can send the message. So we go ahead and say FIFO H, and we send message by message, which is going to be our 8 parameters. And after, at this point, what I'm doing, I'm filling up the buffer. Now we have to do we have to send the command so the scene gets sent. So we send our 0 hex 0C. We do our bit framing. We get our bit framing, I should say, and then here we set the correct bit, which is bit 7, so things get transmitted. Now at this point, everything got transmitted, we hope. So what we do is we wait to see if we go to idle. That means 6 got completed. And then we are expecting to get one message, which is the SAK, and at this point we get the SAK, so which we are going to return, which we are in good shape. So at this point, let's continue with our presentation. So this is what, at this point, we've done everything is required associated with the tag as a whole, applicable to the whole, all the applicable to all the blocks on the card. So from now on, all the tasks that we are going to do are going to be applicable to blocks and sectors. This is applicable to the whole card. So let's continue with the presentation.
Okay, so let's go ahead, and what we're going to look at next is going to be the authorization request, then the code for reading and writing. So now we started here what's applicable to a particular block and authorization for a particular sector. So let's continue looking at the code.
Okay, let's look at the code authorization. So what's going to happen is the card is going to send the authorization request to the tag or to the card reader, I should say, and followed by the block number that it wants to access. So one thing that we have to realize at this point is that the authorization is going to be for all the blocks in a particular sector. So once you get one of the blocks authorized, then you are basically authorized to read or write, or I could say in general, modify any item in that particular, that belongs to the same sector. Next, the tag is going to send a random number back. Using that random number, the card reader is going to run it through an equation where it uses the key, the UID, and it's going to send the result back to the tag. And then the tag is going to run the same numbers, and if it gets the same result, then it's going to send the verify reply, which means that communication or that the card reader can access the tag or the card. And when I talk about the card or the tag, it's going to be synonymous. So let's look at the routine. So we have to provide the routine, the block address that we want to access, the key, and the UID of the tag that we're accessing. So let's look at the command. So the first thing we're going to do is we're going to stop any active command. So we're going to bring the card, you could say in quotes, to 0. We're going to clear all the interrupts, flash the FIFO. And next we're going to send the, so this is just the overhead, and at this point we're ready to send the command. So we're going to send a command to the FIFO data register of 60, which means, hey, we're going to use the key A do all the operations. If we send a 61, for example, that would mean that we're going to use key B. So after that, we're going to send the block address. Once we send the block address, we're going to follow up by sending the key, which are the 6 elements. After the key, we're going to send the UID, which is that identifies the tag that we're communicating with. And here we go and send the 5 words of the key, of 5 numbers of the key, I should say. Next, we're going to send a command that says, hey, what we want to do is authenticate, that's the hex 0E. After we do that, then we have to wait to see that the message got on the other side. Okay, so we're also going to set up a timeout of 20,000 cycles. So we have a do loop here, and what we're going to do is we're going to request the ARQ, which is the state that the register contains the register contains the interrupt register, and if that interrupt register I ended with the hex 10, and it's true that means that the card is idle, which means that the actual request, the authorization request, got sent. So that's where we are right here. Now we also have a timeout just in case for some reason the tag is not there anymore, so nobody's going to answer. In that case, what's going to happen is that the software timeout is going to get to 0, and we get out of the routine with a return with a 1. Now, after we conclude successfully, so we know that the whatever we wanted to do happened. The next thing we do is we figure out, because what happens, we got the verified. So first thing we do is we see if there are any errors, and so we look at we read the register, and we send the error, and end it with hex 13. And if that's true, that means that if we have some kind of an error, could be a CRC error, some kind of communication error, in which case we return it 2. But if we don't have any error, communication error, so then the next question is the proof of the pudding is going to be if the crypto is enabled. That means that the verification, everything worked out, got verified, and therefore the crypto one is enabled, which means we can communicate with the card, and we return a 0. We could say a mission accomplished. So we're ready to read, write, or make any modifications to the card at this point, because we've been authenticated by the tag. So now let's look at reading from the card, which is once we got authorized, now we can do reading. So we got authorized to a particular sector. So for example, if I want to read, try to read from a sector that has not been authorized, so does not belong to a, if I want to read, I should say a block, and it's not within the sector, then this is not going to work. I'll never get the data. So before I can get to this point, I have to make sure that I'm authenticated. So at this point, let's make our message. Let's put together the message. So the first item on the message is going to say hex 30, which means I want to read. So let's look at here. So we have to send the command to read. That's the hex 30. The sectors, this actually should say block. This is a typo. The block we want to read, and follow with the CRC. So we have the command 30, means I'm commanding to read, the block address where I want to read, and then what I do based with this, I calculate the CRC for command 0, command 1, which are 2 items, and the value of the CRC are going to come back to the CRC variable. So I have command 0, counter 0 is the read, command counter 1 is the block I want to read, command counter 2 is the least significant bit of the CRC, command 3 is the most significant bit of the CRC. So I have my command completed between 0 and 3. So now I'm going to do some of the housekeeping before I send the message. So I'm going to make sure that I'm going to stop all active commands. I'm going to clear the interrupts, flash the FIFO. Next, I'm going to go ahead and set the bit framing to 8 bits, because I don't know if the routine before it sets it to 7-bit command, so I'm just making sure that it's going to be an 8-bit command. And after doing that, I go ahead and send my data to the FIFO. And that's my 4 messages, 0 through 4. Next, now I have the data on the data FIFO. So what I do next is set up the transceiver, and then I go and access the command register. I access the bit framing register, and I want to put a 1 on bit 7. Now what I do is I get the whole register here, place it on temp, then I modify the 1 bit I want to modify, and then send it back. What I want to make sure is that I don't modify the whole register. I only want to modify 1 bit on the bit framing register. So that's why I go through these 3 lines. Okay, so at this time I'm going to the data. It's on its way. So now what I'm going to do is I'm going to wait for the task to get done. So first I go and use my routine that I explained before, the RC552 wait _RX idle. So I wait for that, and if the reply is not 0, then I return with a 2. That is, I have a problem with this routine. Next, if everything got accomplished, then the next question I have to make sure, was there any type of error, CRC error or whatnot. And so I check this register, the error register, and I end it with 1B. And make sure I get a 0 here. So that makes it jump to this line. Now I know I'm going to get my block is 16 bytes, I should say, plus 2RC, that would be 18 bytes. So at this point I'm going to say, okay, so in theory I got my message. Now let's make sure that's true. Hey, is the length of the message 18 bytes? If the reply is yes, then if it's no, then I'm out of here. If it's yes, that means I got my 18 bytes. I'm going to go and grab my 16 bytes, which is what represents the block. And then I'm going to discard the other 2, which are the CRC. So I just go ahead and read the FIFO twice. So there you have it. So this the buffer sub I, which is what I'm returning here, the asterisk buffer, to whoever called the routine. So I'm getting the contents of the block. So now let's go ahead and do the code for writing a command into the tag. So again, all this got accomplished once we get the authorization. The authorization we're going to write into the correct block that has been authorized. So again, this is kind of a typo, but in reality, if I put any block, any address, all the elements within that are contained in this particular block where I'm requesting, all the elements contained on the same sector are covered by the authorization. So let's look at this. So I'm going to send the write command, the sector, and the CRC. So let's see how I do that. So right here I have my first element of my command. It says, hey, I want to write. So that's the hex alpha 0 is the writing parameter. Next I have my block address. Then so we have command sector or block, and then we follow by the CRC. So now that I have these two elements, I have to calculate my CRC. So I use my routine that I send it to the card reader and use the facility of card reader that to calculate the CRC. So I call the RC522 calculate CRC, which I send the command which contains command 0, index 0, command and index 1, which are two elements, and then the CRC, which is going to come back with the CRC, the two CRC numbers. So if this doesn't come back, we say this comes back, we say 1, then I return a 1, which means something went wrong. If it returns a 0, that means everything worked out. So I'm going to, in my command array, which has 4 elements, so what I'm going to do here, I'm going to say command 2 is going to be the CRC low, least significant bit, and then the CRC most significant bits. So now I have this complete message, my write command sector and CRC, which I'm about to send to the tag. But before I do, let's do some of the housekeeping. So we're going to make sure that stop all running commands, clear all internal interrupts, internal interrupt flags, I should say, clear interrupt flags. Then we're going to flash the buffer. And then, of course, I'm going to make sure that I reset to make, we have an 8-bit framing. Now, I do that because I don't know if the routine before me, I set up to a 7-bit frame. So I have to make sure, just in case I'm going to set up again. If it's to 8, that's fine. In any case, I'll do it again. So at this point, I'm ready to load the data into the FIFO data register. So I had my 4 elements, so I have from 0 to 4. I do my my loop, and now I have all my commands got loaded into the FIFO data register. So next, I do what I've been doing before. To send the message, I set the transceiver command. Then I place a 1 on the bit 7 of the bit framing register. And as before, I first get the parameter, then I change it, then I send it back to make sure I only modified the 1 bit, I leave the rest the same. So at this point, I'm going to send this command. So I'm going to send the write command, the sector, and the CRC, and that's what I just completed here. So let's get into my do loop. So my do loop is going to go around until the system goes to idle, or it says that the data when the system goes to idle, or the commands got completed. So if for some reason the tag goes away while I have my timer with my 20 cycles, if nothing happens there, then I'm going to go out of this loop. So if I'm successful here, the next thing I'm going to do is I'm going to say, hey, I'm going to see what's on the FIFO, and what I'm expecting to see is one message, which is the hex 08, which is the acknowledge message. So I say, hey, do we have one message on the FIFO? And the answer is yes. Then my next question, hey, is the message that is on the FIFO, is it that equal to 0A, which is the acknowledge? And if the reply is yes, then that means that I'm that I got the command completed. So so I'm right here at this point. So now what I need to do, I need to set up my I need to send the data plus the CRC, because I just got my acknowledgement here. So let's start putting the the command. So I have my data. So what I need right now is the CRC, so I can send my data and the CRC. So once at this point, hey, I got my acknowledgement. So the next thing I'm going to do here, I'm going to calculate the CRC for my data, which are 16 elements, because that's the size of each of the block. So, okay, so now I have my my CRC, which are located on CRC0 and CRC1. So now what I'm going to do is I'm going to go ahead and do my housekeeping before I send any message. So I'm going to stop all the commands. I'm going to clear the register. I'm going to flash the FIFO. So at this point, I've done all my housekeeping, and what I'm going to do is I'm going to send I'm going to put the data, and I'm going to send it. I'm going to put the data into the FIFO. Into the FIFO. So this is the 16 bytes. I load them into the FIFO data register. So I have my data, and I'm right here. So I got my command. I'm right here. I'm sorry. I have my data already loaded, and now what I have to do is load the CRC. So at this point, so I load my data. Then I have my CRC, which I already calculated, and they are in CRC. I calculated right here in CRC0, CRC1. So following all the data, I send it to CRC. Then again, I am going to, so everything is set up on the FIFO. Now I have to transmit it. So I go and start the transceiver, and then I go to my bit framing register, and bit 7, I'm going to put a 1 there. And again, as before, I go get the data, I modify the 1 bit, and then I send it back, leave the rest alone. Okay, so at this point, I send in my data plus the CRC. I'm right here. So I do that, and if I get the hex 31, that means that I was successful in sending the data. Next, I'm going to go ahead and see what I got back, and should be one message, and should be the acknowledged message. And at this point, I know that I transmitted my data and I returned 0. Now, as far as my my picture shows here, so I did all this, but I somehow left out my last acknowledgement. And then I put these 2 items, which meant, hey, after you send a command to write, you have to always, next step should be just ask to read the data from the blocks that you just wrote into, to make sure everything got accomplished correctly. So anyhow, that let's go back to the presentation to continue.
Okay, so we're back, and so now what we're going to do is show the code for terminating the exchange. The idea here, as I mentioned before, we have to make sure that we do one transaction with that card, and we're not going to do anything else with that card until the card is removed and another card is placed, so the same card comes back. So let's look at the code to get that accomplished. Let's look at the code for terminating the exchange between the card reader and the tag. The idea here is that we've performed all our transactions, and now the tag, after that's concluded, the tag may still be there, or we don't know when they are going to remove the tag. So the idea is here, okay, we did the transaction, let's terminate everything, so we don't do the same thing over with the same card again. So let's see how we do this. So first we have the we have to send the command to halt the session, and that's sending the that's hex 50 and followed by 0. That's the first command, and then we're going to send the follow. It's going to be the CRC. So we call the CRC, and we get this CRC 0 and CRC 1, the most significant, least significant part of the CRC. Next, we're going to do our housekeeping. We stop every command. We clear all the interrupt register. We clear the FIFO. We flash the FIFO. Then we set the command to be a 8-bit command. Next, we send our data. I should say we put the data into the FIFO data register, which are the 4 elements. And we start the transceiver, and then set the bit framing bit 7 to 1. And as usual, we get the whole register. We modify the 1 bit, and then we send it back. So at this point, we've sent the whole command, and now we have to wait for it to be completed. So what we do in the while, we're going to check for hex 30, and IRQ is equal to 30 and not equal to 01. So at this point, if we complete this, then we are successful, and we return the 0. So that takes care of the halt. Now we have another thing where we're going to call end the session. What we're going to do here is we're going to also, in addition to sending the halt command, which we're doing right here, we're going to clear the crypto. So let's see how we do that. So we set the halt command first, then we set the system back to idle, and now what we want to do is disable the crypto. So we get the whole status register, and we end it with F70, which clears the crypto. Next, we send it back. Then after that, we're going to clear our interrupts, flash the FIFO, and reset the framing to 8-bit. So basically, ending the session is stopping the crypto. And I have one more, which is going to be here to actually stop the crypto. So in that case, we just do the 3 steps we did up here, which is we get the status 2 register. We end it with hex F7, and then we send it back. Clear the 3 bits for crypto, and then we write it back. So the idea here is to have different routines that we are going to use with the purpose of shutting everything out, whether the tag is there or not. So let's continue with the presentation. Okay, so let's. So what comes next is we have all the ingredients. We can read, we can write, we can authorize. We see whether the tag is together. But now, what we're going to do here is how we're going to put the whole thing together. So how we're going to go about doing all the various tags, various processes, and so let's see how we go about doing that. So let's go ahead and review the code for managing the RFI transactions. So what I did here is I created a type def which contains all the different states that we're going to have to go through to get a successful RFI transaction. So we have the idle, wait for tag, and the collision, select, authorize, write, read,
next block, hold, cleanup, removal. So the routine responsible for doing this task, managing this task, I should say, is RFID underscore tasks. Now this is the main program, and the RFID underscore task is going to be included in the infinite loop. So let's look at the routine. So basically what I'm saying is this routine is going to be called over and over and over. So let's see how this works. So I went ahead and hard-coded some items just to simplify things. So I have the initial state is going to be idle. Then we can select between mode read or mode write. We're going to go ahead and select mode write, and the reason I do that is because every time we write, we're going to read to make sure that everything worked out okay. Next, I have something called the current block and the last block. So when we do reading or writing, we may select one or more blocks to read or write. Now, as I selected the mode write, then the data we're going to write into each of the blocks between 58 and 61 is going to be Andrew RFID test, and then finally I have the key which we are going to be using, the default key. One of the things that I want to mention is that we're not going to be writing into or reading sector trailers. If we want to touch the sector trailer, we're going to do separately because we don't want to by mistake trash one of those sectors and then we don't have way to access that sector again. So let's continue. So I put this as a reference so we have it in the back of our mind. So here we're going to have a switch, and we're going to be able to switch into the different states. So for each state, what I've done is I go ahead and I display in the laptop the state we're in, and that's just so when we do the sample, we'll be able to see how we jump from one state to another. And then each time you go to a state, you're going to perform a task, and then if successful, you're going to go to the next state. So let's see how this works. So we come into the state idle, which was set up, and the first thing we change is to the state wait tag. That means wait for the tag. In the state wait tag, we're going to send the WPA, and if a tag is detected, then we go ahead and display, of course, that the tag was detected, and we also change the state to state anti-collision. Next time we go in, don't forget we're in the infinite loop. we're going to be in the state anti-collision, and what we do here, we call the routine anti-collision and get the UID. And if this is successful, then we change to state select. If it's not successful, we stop everything and we clean up. Next, we have the state select. In the state select, what we're going to do is we're going to select the card using the RC522, and then we're going to change the state to authorize. Now, I've hard-coded here the first state we're supposed to read, but it should really be a variable, but I'm simplifying as much as possible to make it clearer. So we change from here, we change the state to authorize. In the authorized state, what we're going to do is we're going to send the current block, the key, and the UID, which is information we already have. And of course, at this point is where we start talking about this is associated for the current block and all the blocks within the sector. That's what we're authorizing. So if the authorization is successful, then we set the mode to write. If the mode we selected was write, then we change the state to write. Otherwise, we change the state to read, and if something goes wrong, we clean up. So let's look at the write state write. So in this state, what we're going to do is, first place, we're going to write the data. And if the write necessity is successful, then the next thing we're going to do is we're going to change the state to state read. So we wrote the data, now we want to read it back, make sure it's correct. So in the state read, what we do is, of course, we read the data, then we're going to display the data on the laptop. Now the display of the data we're going to do in two different ways. We're going to display the hex values, and we're going to also display the ASCII. And after that, we're going to go to change the state to a state next block. So we don't know how many blocks we need to read. So we go to the next block. Now here we're on the next block. So what we're going to do here is, first thing we do, we increment the block. Let's go get the next block. After incrementing the block, we mod it with mode. If the result is 3, then we know we are at the sector trailer and we want to skip it, so we increment again. Now, if you take the sector trailers are basically 3, 7, 11, 15, 19, so forth and so on. And every time you mod it with 4, you're going to see that the result is going to be 3. Okay, so at this point, if this is not true, that means we're not at the sector trailer, so we can go ahead and make our next check. And even if we're sector, we increment the block. So after doing all the incrementing, we incremented once. If it was sector, we incremented again to skip it. Now at this point, we're going to ask the following question: is the current block greater than the last block? And if that's true, that means that we've done all the reading and writing we're supposed to, and we just change the state to state hold, and we break. Now, if this is not true, then what we have to do is we need to find out whether or not this block is the first block in a sector. If it's the first block in a sector, that means we've jumped from one sector to another, in which case we need to reauthorize again. So, okay, is this the first element? Is this block the first element in the sector? If yes, then we change the state to authorize, and we're done. Now, if that's not true, then what we do is we change the mode for, if the mode was write, then we change the state to write, else we change to read. Now, once we're done doing all the writing and reading from here, then we go to state hold. In the state hold, what we're going to do is we're going to call our routine to hold, and then we're going to change the state to cleanup. In the cleanup state, what we're going to do is we're going to stop the crypto and end the session. And then we're going to change the state to wait for removal. And so here we are, state wait for removal. So what happened is we read the card, we wrote and read the card, did the transaction, I should say complete transaction, this particular card, and we don't want to do it over on the same card. So what we need to do is we need to wait for somebody to remove the card and then wait for a new card. Or the same card, but if you want to do the same transaction, the first same card, you need to remove it first. So what we do here is we have a counter, and we use the counter, so we want to make sure that the card actually got removed, so we double check everything. So we have a counter which is going to let's start with 0. So we put everything into idle. We flash the FIFO, and then we're going to use the WPA to see if the card's still there. But so that command is a 7-bit framing. So we need to do 7-bit framing as before what we've done. And then we say, hey, is the card here? And if the answer is, if this is successful, that means that the card is still there, the same card. If it's not successful, then we increment out the counter, and we go back to state wait for tag. We don't change the state. Then we do this over and over till we have 5 consecutive. The card is not there, and then we can change the state to state wait for tag. So we once the greater than 5, we are certain that the card is not there. Then we go back, start from 0, state wait for tag. Now, one thing that I did here is I added a delay of 1 second. So I did that so when we go through the example, we're going to be able to see the display. Otherwise, the display goes so fast we cannot see any of the data. So that's why I put a second so we can see what's going on. So let's go ahead and go back to our presentation and see the sample program.
Okay, so let's go to the sample program. So what we're going to do is first we're going to wait for a tag to show up. Once a tag is detected, then we're going to modify block 58 through 61. We're going to write Andrew RFID test. Then the writing will require the authorizations of sector 14 and 15. So basically what I'm saying is, hey, we're going to start in 58. So we're going to read 58. Then we're going to try to read 59, but it's going to be, we're not going to do nothing there because that's a sector, I should say that's a sector trailer. So we read 58. We get into sector trailer. We should do that, but skip it. Then we get to 60. But before we read to 60, we have to get reauthorized, and then we can read 60 and 61. That's what we're going to be doing. And our setup is going to be, we have our ATMEGA 328 microcontroller, and we have our SPI connection and a reset, and then we'll have our connection to the laptop. So let's go ahead and look at the sample program.
So I'm going to go and give you a highlight of the program, and then we're going to look at the outputs, because we have already reviewed this code. So we have here, we're defining our enumeration type. Then we initialize ports, initialize SPI. We have SPI transfer. Then we write register, read register. We have the initialize the reader. Next we calculate CRCs. We get the version. We wait for the idles for the different transaction. A routine for the REQA, routine for the WPA. And again, we've already looked at all these routines. I'm just enumerating them so you can see the whole thing together. We have the anti-collision, the select, authorize, and read routines. So followed by the write routine, and we have the hold routine, end session, and then we get here into our RFID task, which we just looked at, all the different tasks that we have to accomplish. And next we have the create access bytes. And finally we have our main program. In our main program we basically do all the initializations and send the hello world and the version, and then we get to our infinite loop where we call the RFID underscore task over and over. So let's look at the output of these routines. So here we can see I'm powering up the processor, and we have our reader here. And I'm going to go ahead and put the card. When we put the card, then we get the output. We write something to the card and write in the output. Next, we wait for the removal to verify the removal has been verified, and then I use a tag to do the same thing. And you can see the UID and the output from what we printed. So what I'm going to do next, let's look at the output. Actually, let's look at the output from the display so we can read what's coming out. So this is the actual display, and we're waiting. So let me stop here for a minute. So we have here the state, wait for tag, and then the tag detected. Then we have the anti-collision, it was successful, so we have the UID here. Then we go to state select, and we have the SAK3, and after that we need to get authorized, and we're going to write into the block, and then we read whatever we wrote, which is we started block 58, and we have Andrew RFID. So this is the hex, and this is the ASCII. We go to the next block, but the block 59 is a the block 59 is actually a sector block, so we need to skip it. So 58, we skip 59, but then we get into block 60. But block 60 is the first block in the new sector, so we need to authorize. So we got 58, we skip 59, then 60, we actually authorize, and here shows authorize was successful. Then we go to state write, and what we're doing is writing into block 60, and then we read, block 60, and then next we go next block, and then we write again, but this time we don't have to authenticate like we did here after the next block. So we go ahead, next block we write, and then block 60. So let's continue with this, and then we got into hold cleanup and wait for removal, and then so let me go back all the way to the start so we can see what we did from the beginning. Okay, so we started with Hello World, then we had the chip type software version, and then we started in state idle, and then we went to state wait for tag. Next, as I showed, we ended up with the tag detected. We have the UID of the anti-collision, SAK3. We authenticate, we write and read. We go next block, and then we skip that block, then we are in a new sector, we authenticate, and then we read 60 and we read 61. Okay, so at this point, let's go back to our presentation. I think you've seen you got a good idea of the output.
Okay, so now we got to finally got to the summary. It's been a fairly long presentation. So today I gave you a description of the RFI receiver and transmitter. We looked at all the code to make these transactions, to enable those transactions. We went through a sample program. So now we're on the summary, of course. So I would like to thank you for spending the time with me. I hope you enjoyed it, and I'll see you soon. Thank you very much.